So welcome to the final lesson of this course, which is on derivations in predicate logic. So we'll be continuing to talk about the predicate logic that we first learned about last week. But this time we're going to be doing, instead of translations or just explaining what the symbols mean, this time we're going to be doing derivations. All right, so let's see how this goes. So first note that most of our rules and derivation types from propositional logic are still going to be usable in this derivation system with predicate logic. So we're still going to have things like modus ponens or double negation elimination or addition, all those rules of direct derivation we used. And we're also going to, we're going to still have direct derivations, we're going to have conditional derivations, and we're going to have indirect derivations, just like we already had. And we're going to still be able to nest all kinds of derivations as needed, just like we were with propositional logic. So we're keeping all our rules, all our derivation types. We're just adding in some stuff. So the first thing we're going to be adding in is our first new derivation rule is going to be called universal instantiation. Okay, and it is pretty straightforward, I think. So what the rule is going to let us do is take a universal claim. So for example, for all x's, x is an f, or everything is f, basically. And we're going to be able to get rid of the quantifier, which we'll need sometimes. If we're trying to prove a particular claim like c is f, we might need a way of going from a universally quantified claim like all x's are f to the specific claim about the constant. Anyway, this will become apparent to you as we go, but first note that you'll remember all x f of x means that for any x, anything, whatever x is, it's going to be an f. X is an f, right? So we know that everything is f. Everything that we can talk about in our language is f. So we can plug in any constant for the variable x if we already have for all x's f is an x, or x is an f. So we can plug in any constant and eliminate the for all x part, right? So using universal instantiation, we can go from this big universal claim for all x's, x is an f, and we can just say, well, any constant, in this case c, is f, right? Because everything is f. That's what the all x claim is saying. And so we can just get that, some particular thing, c in our case, is f. That's the universal instantiation rule. We take this universal claim, all x's are f, and we instantiate it in a particular case. Well, c is f then, if everything is f. Yeah, and this is what it will look like in our derivation system. I will show you in a moment. After we talk about one more rule, I will do some examples, but here's one instance. So we're trying to show that, c is f, whatever c is. And we already know as a premise that all x's are f, or anything is f. So as usual, we write our show line. We're trying to show that c is f. That's line 1. Then we, of course, list our premise. All x's are f. For anything, it's f. And then we can immediately just apply our universal instantiation rule to line 2, where we have this universal claim. And we can pop out c is f. And you could use this for any constant. You could plug in any constant where we have c on line 3 here if you had to. But we're trying to show that c is f. So we just use the universal instantiation on line 2 to say, well, if all x's are f, then of course c has to be f, because c is one of the things that x could be, because x is a variable and c is a constant. And there you go. As usual, you get what you were trying to show, so you close a direct derivation. It is a direct derivation because, we made it appear directly in the proof using a direct derivation rule. So there you go. Okay. And then the second rule we're going to add is existential generalization. We're going to call this EG, right? This rule lets us make a sort of general claim using a constant we have. So for example, if we already know that the constant C is F, right? It has whatever property F is. C is F, is what this basically says. Then we can generalize this claim out, right? Because if C is F, then we know that some constant C is F, right? We know that there is a thing, C, which is F. And this tells us that there's at least one thing, which is F. And you'll remember that's exactly what our existential quantifier is saying. There's at least something which has this property, right? There's at least one thing. Well, if C is F, then we know there's at least one thing which is F, it's C. So as a result, if we have C as F, we can get there is at least one X which is F. There is at least one thing which is F, right? And that would be the EG rule, existential generalization. We take this constant claim and we pop out an existential generalization. There is at least one X, which is F, because, I mean, we already know C is F. Okay. So here's how it looks in a fairly basic form. So, suppose we're trying to show that there is something which is F. There's at least one thing which is F. And as a premise, we already have that C is F. Well, we write what we're trying to show, of course. We list our premise. And then we can just apply existential generalization, e.g., to line 2. Because on line 2, you see, we already have, well, C is F. And so with existential generalization, we know that there's at least one thing which is F, because we already know C is F, right? So we can just pop out, there is some X which is F on line 3 by applying EG to line 2. And then again, it's a direct derivation because, we made it appear directly in the proof using a rule of direct derivation. There you go, it's a direct derivation. Okay, great. So now I guess we'll do a few Carnap examples using these new rules. Okay, so as you can see, I've already pulled up as always, the Brightspace lesson, which is lesson 12 in this case. And we're going to open the chapter 12 practice document and we'll go look at that. There is also this extra practice document. You'll only want to look at that after you've watched this whole video because you still need to learn some stuff to do the problems on that extra practice. So we'll just start with my practice document we made. Okay. All right, well, let's do the first one. So these are more complicated examples of the kind of where we use the rules I just showed you in their simplest forms, but now we're going to apply them a bit more complicated. So in this case, we're trying to show that there is at least one thing, one X, which is both G and H. That's what we're trying to show, right? And our premises are that C is H, and C is also G. So you can see here we have C is G and C is H. But we need to get this existential quantifier claim, right? So how are we going to do that? Well, we know that with our existential generalization, we can put this existential quantifier in front of something that we already know. I mean, assuming all the constants are the same, we can just put one there. So let's do that. We want to get a Gx and a Hx, right? But we want it all to be in one phrase so that the existential quantifier can just go in front of it. So what we're going to do is we're going to look at what we have here. Well, we have C is G and H is, or C is H. So, I mean, already in our minds, we know C is both G and H. So let's put those together using our rules that we're already used to. In this case, it would be adjunctivization, and it would be on lines 2 and 3, right? Look at that. Well, now we have that C is G and C is H all in one completed phrase, just like we're trying to get here. Now we can generalize out into an existential claim, right? Because we know it's true for at least one C, for at least one thing, namely C, that it is both G and H. So let's generalize that out, shall we? and get what we were trying to show. So, we know it's true that there is some C which is G and which is H. So, of course, we know there's at least one thing which is both G and H. So we just use the existential generalization rule. And look at that, we've completed the derivation on line 5. It's pretty good, right? Okay. What's another good one to start with here? Let's use this one. Okay, 1.3. So we want to show that A is G, right? And A is a constant. It's not a variable because we know the letters at the beginning of the alphabet are constants and the letters at the end are variables in our system. So there is something A. We know that something called A is G. It has whatever property G is. That's what we're trying to show. So now, as always, we list our premises and we are good to go. All right. So let's think here what we can get. Well, we're trying to get that G is A, right? And we have this claim that all X's are either G or they're H. It's true for all of them. Well, one thing we could do is take this not HA, so it's not the case that A is H, and reject this side of a modus ponens if we can get this to say A, right? Or we can reject this side of a disjunct using modus tollendo ponens. If we can get this to say HA, right? And then that will give us the left side. So let's try and force this all to be about a, right? Because we know everything, for all things, that's what this is saying, for all things, it's G or it's H. So we can use our universal instantiation rule to make this a claim about A's, right? So we'll say G, A, or HA, and we're using universal instantiation, UI, on line 2, right? Look at this. Now we already have our not HA, so we have the negation of the right side of a disjunct, and we know that lets us get the left side of the disjunct by using modus tollendo ponens, right? MTP, using lines 3 and 4. And then finally, again, we got what we were trying to show, right? We were trying to show GA, and we got GA. So now we can close our direct derivation on line 5. Let's see, what would be a good one? Try and save some of the harder ones for you guys. But what would be a good thing to start with? Let's do one more kind of simple one just so we get our heads around it. Or this one is interesting, actually. Let's do this. So we want to show this whole thing. And we have FA as a premise. All right. This one's kind of fun. Because, what's the main connective of this show line, right? The main connective is this OR claim. And how can we get an OR claim? Well, you'll remember with our addition rule, our ADD rule, if we get one side of this OR claim, we just get the whole OR claim for free, right? If we know one side is true, then, we can say the thing we know is true or something else is true. And that whole claim will always be true because we know one side of it is true. So what can we do here? Well, we have this FA as a premise, right? Which means we know that there is some constant A, which is F. There is something which is F. But this lets us say, well, there's at least one thing which is F, right? Namely, it's A. But we can generalize out into an existential quantifier claim because we know there's at least one thing which is F. So let's do that. Right? We already have, well, A is F, so we know there's at least one thing which is F. There's at least one X which is F. And then we can just get this for free, right? Using one of our old trusty rules of direct derivation, the addition rule on line 3. Because if we have this side, we can just stick a OR symbol and whatever else we want on the other side for free. So there, we got exactly what we were trying to show, and we can close the derivation now. Good. All right. So there's lots of harder problems to try. I would suggest, working through these slowly. If you have questions, ask your TA at your tutorial or whatever. Yeah, this will help you for the final exam. Okay, back to learning more about derivations in predicate logic. All right, so you can see now that we have developed two derivation rules that we can use to eliminate a universal quantifier with UI, right? We take a universal claim and then we instantiate it into a particular case, right? And also we have a derivation rule that lets us introduce an existential quantifier, right? So we know something is true about a particular case, and then we can say, well, then it must be true of at least one thing that this is the case. But sometimes we need to prove a universal claim, right? Like we don't want to eliminate it. We want to say, oh, all things are this. Or as part of a proof, we might want to eliminate an existential quantifier. Or we might want to more likely use that existential quantifier in some particular way towards the ends of proving something else. So in that case, it's not that we're introducing an existential quantifier, but we need to be able to use it somehow. So we're going to introduce two new types of derivations. So these are not rules of derivation, they're types of derivations. And these are going to be universal derivations and existential derivations. Okay, so if we want to prove a universal claim, so for example, we want to prove that for anything it's f, for all x's, x is an f, we'll do a universal derivation. So to start, we need to make use of a fresh constant. So a fresh constant is a constant, so one of those letters from the beginning of the alphabet, that is not already used in the proof at all before we make use of it. If you use the constant anywhere else before where you're introducing it, it's not fresh, and it's not going to be usable in this universal derivation. So we need a constant that is not in any earlier lines, not in any show lines. It needs to be fresh. So the idea is that, well, we introduce some random constant, let's call it C. And then if we prove something is true about C, this random thing we pulled out, then it's true for any arbitrary constant we think of. It's true for any random thing. And so we can say, well, then it's true for all x's, right? If this thing has no particular special properties that would differentiate it from anything else, it's just some random new constant, then, if it's true of that, it's going to be true of any arbitrary constant. So that's the idea. So a universal derivation works by saying that we'll show some universal claim. So like normal, you write a show line. And then you have to write another show line with a fresh constant to show it. So you're going to say, well, in this case, for example, you can see the example I've given you. Really, we want to show that for all x's, for anything, if it's f, then it's f. For all x's, if x is an f, then x is an f. So, we write that at the beginning. And then we write a show line with some random arbitrary constant, in this case c. It's fresh, it hasn't been used at all in the proof before. And then we prove this claim using some, this claim that we've set up with an arbitrary constant, a fresh constant. And if we can show that, for this random arbitrary thing c, it's true that if it's f, then it's f, then it's going to be true for everything. So you can see, we have this large universal claim we want to make. We decide, okay, well, if we can show it's true for some random arbitrary constant, in this case c, which we do, we show, if you have c, if you assume c, because we're doing conditional derivation, right, where the arrow here is the main operator. If you have c, you assume c is f, then you get c is f, right? It's the same line. So you close your conditional derivation, and now you've shown for some random fresh constant C that if it's F, then it's F. So then you can close your universal derivation using what you proved about the fresh constant. So on line 2. And then that gets you finally this thing you were trying to show at the beginning. So, I mean, it looks a little complicated, but as you do the practice and as you watch me do some practice, it shouldn't be too bad, I think. But before that, we're going to jump into also introducing existential derivations. And these are a bit maybe trickier, in my opinion, but actually could go either way. Anyway, existential derivations. Okay, so sometimes we want to prove a particular claim using a line with an existential quantifier. So, you'll remember if there is some x which is f, there is at least one x which is f, there's at least one x where that x is f, right? Then you know that there's at least one thing. And we want to be able to talk about that one thing in a proof sometimes, right? So if there is at least one x which is f, you might want to discuss whatever x it is actually f, right? And we need a constant for that. We need to talk about one particular thing. So, if we're going to use this as part of a proof for something, first we start by saying what we're trying to prove. Then we give a name to the x which is f, because we know there's at least one. And again, we have to use a fresh constant when we're doing this. So it has to be something that is not already in the proof somewhere. And then we assume that, this fresh constant, in our case, we'll use C, is f, because we know at least one thing is f. So whatever that thing is that is f, we're just going to call it C. We're just going to call it C. And C has to be fresh, of course. And then, we go on and we prove what we're trying to prove. And then at the end, this is the difference from the other derivation rules we've had and the derivation types we have. At the end, we have to cite 3 lines when we close our derivation. So we have to cite the existential quantifier line we used that we then made like a claim about the constant it's about. So we have to talk about the existential quantifier line, which in our case is going to be something like there is some x which is f. We cite that one. And then we cite the fresh constant line. So the line where we assumed something about a fresh constant, which in this case would be C is f. And then finally the line where we got what we were trying to show. Okay, so here is an example of an existential derivation. All right, so as you can see here, we are trying to show the claim that there is some x which is g, right? That's what we're trying to show. And we're going to end up, we have these 2 premises. There is some x where if x is f, it has to be g. And for all x's, we know that x is f. Okay. So how are we going to prove this existential claim that there is some x which is g? Well, we're going to do an existential derivation. So we're going to say, well, we know that, there's at least one thing where if it's f, it has to be g. So we're just going to call that thing C. We're going to give it the name C as a constant. Notice at this point, C has to be fresh. It has to be a fresh constant, right? So we write in, well, C is f. If C is f, then C is g. We write that this is an assumption we have because we're assuming this about C with regards to the fact that we know that there's already at least one thing for which this is true about. Great. So we've set that up, and now we need to somehow get that there's some x which is g. Okay. Well, with universal instantiation, which we learned earlier this lesson, we can take our universal claim on line 3 and instantiate it with whatever we want, right? Because we know that, if it's true that all x's are f, well, then C has to be f, because C is one of the things that x could be, right? So then we say, well, C is f by universal instantiation on line 3. That's great. And then look at that. On lines 4 and 5, we have the recipe for a modus ponens. So we apply that, and then on line 6, we get C is G, right? We know that for the constant c, c is g. Okay. Well, that's great, because then we can apply our existential generalization rule that we learned earlier in this lesson as well to say, well, if there's one thing which is g, namely c, then we know there's at least one thing which is g. Great. And that's exactly what we were trying to show, right? So at that point, we can close our existential derivation. And you'll notice that we cite 3 lines. We cite line 2 because we used line 2 to make our assumption on line 4. Line 4 makes an assumption about the thing that line 2 is about, right? Because line 2 is saying, well, there's at least one x where if it's f, it's also g. If it's f, it's g. And then on line 4, we said, well, let's assume that that thing is c. Could be any arbitrary constant, but we'll call it c. So that's why line 4 is cited. That line 2 is the existential claim we used. Line 4 is where we made the assumption about that claim. And then line 7 is just where we got what we were trying to show. So those are the 3 lines we cite. Okay, good. So let's do a few examples now in the Carnap system using our two new derivation types. Right. So you can see we're back on the same practice document. We just scrolled down a little bit, down to these universal and existential derivation practice questions. This first one is one that we already did. It's the one I showed you in the slides, so we'll skip it. But you should work through it so you make sure you understand how it works. Anyway, let's go on to this one. So as always, we write what we are trying to show. And then we put in our premise. And there we go. All right. So what we're trying to show is a universal claim, right? So we're going to need a universal derivation. So if we can show for some arbitrary x, it's f, then we can pull that out using our universal derivation, right? So first we're going to show that, well, for some arbitrary c, it's f, right? Conveniently, in our premises, and the c also I should say is a fresh constant. Okay. Now conveniently for us in our premises, we already know that for all x's, they're both f and they're g. So we can use our universal instantiation rule to say that c is f and, oops, my French keyboard was on, and c is g. That would be universal instantiation on line 2, right? And then conveniently with our and symbol here, we know that we can simplify it into either side. So we will simplify line 4 to get fc, right? Well, now we've shown that fc using line 5. So we've shown that for some arbitrary c, it's f, which means we've done a universal derivation where we got to show that, for some arbitrary thing that was a fresh constant when we started it, it is f. And so we can close our universal derivation with line 3. And there you go, correct proof. Okay, good. Okay, so let's do another one. Let's do 2.3. This one, it looks like, is going to be an existential derivation, but let's find out how we're going to do it. Oh, actually, this is the same one I already showed you, so we'll skip that one as well. And let's jump straight to 2.4. Let's get our premises out. Okay. So what can we do here? Well, if we're going to do an existential derivation, I mean, really what we need to get is that there is some c or some constant which is not f, right? Well, one way to do that is to take whatever it is here that is not g, because we know it's true that at least one x is not g, right? We know that. Then if we can use that to get a not f the same thing as not f, right? Because we can pull this out and do a modus tollens on it, as you'll see in a moment when I do it. Then we can get that there is some C, let's say, which is not f. So, I mean, we know we're going to need to do some sort of existential derivation here. So let's pull out a fresh constant and assume, the thing which is not G, because we know there's something which is not G. That thing is C, we'll call it. We're going to make that assumption, right, using this. Well, we have a universal claim here, and we know with our UI rule, our universal instantiation rule, we can say for any x, whatever it is, so C in our case, because that'll be useful, if it's f, then it's G, right? So we're going to say, well, if C is f, then C is G. And that is from universal instantiation on line 3. Okay. Well, we have this arrow claim, this if-then claim, and we have the negation of the right side here. So we could do modus tollens to get the negation of the left side, right? So we're going to get not FC by modus tollens on line 4 and 5. And that's great because we wanted to get that there is some x which is not f. And look, we have it right here, right? We know that this thing C that we've been talking about is not f. Whatever C is, we know it's not f. So we know there is at least one thing which is not f. We did existential generalization on line 6. Great, and that's exactly what we were trying to do. You can see I left in all the brackets, but this is abbreviated. I left in the brackets. I prefer to leave in the brackets for clarity on these quantified logic ones, but anyway, the point is, we got here what we were trying to show. So we can close our existential derivation. And we know it's an existential derivation because we had to assume, C was the thing that line 2 was about. Anyway, so what are we citing? Well, we're citing 3 lines. So first, we have to cite the existential quantifier line that we used, which was line 2. Then we have to cite the line where we made the assumption about the thing that line 2 is about. So in this case, that's line 4. And then we have to cite the line where we got the conclusion, which is line 7. And there we go. We close the proof. Okay, good. All right, let's do one more. You can see 2.5 and 2.6 are actually the same. So we'll just do 2.5. Sorry about that. And as always, we list what we're trying to show and list our premises. Okay. Now, what we're trying to show here is a negated claim, right? The main operator here is this negation symbol. It's saying, all of this is negated. I will get rid of those brackets just for, I don't know, whatever. The point is, it's saying all of this is negated. How can we introduce a negation? Well, doing an indirect derivation. So at some point, we're going to have to do an indirect derivation, right? But it might be wise to first take a look at our premise here before starting our indirect derivation. Because if we're going to make use of this, we want to make sure that any constants that we introduce are fresh when we want to make use of this first, right? So let's do that. Now we know if in this depth of the proof, right, because we haven't nested anything yet, we're just like one line deep, right, one indent deep. But just by making this assumption, we know that this line is going to close with an existential derivation because we make this assumption to do an existential derivation, right? So if we want to do an indirect derivation, we have to open another line. So let's do that. We have to open another proof, I should say, a nested proof. And really, we're just going to prove, the strategy we're going to take here is we're going to prove what we're trying to show ultimately, but we're going to prove it in a nested proof and then use it as a sight line in our nested derivation, in our existential derivation. So you'll see at the end, but just Stay on board with me, and you'll see at the end. And then if you walk through the steps yourself, you'll start saying, "Oh, I see why this is happening." But anyway, okay. So for an indirect derivation, we always we're trying to prove the negation of this, so we assume this, right? Great. Now we have this C as F up here, right? But if we have this assumption, then we know that all X's are not F. And that's going to create a contradiction, right? Because it's clear that here's an X, namely C, which is F. So let's pop out this using our universal instantiation rule and get not F, C, universal instantiation on line 5. Great, right? Okay. But this, not FC and FC, they contradict. So we can close our indirect derivation, right? Using the contradicting lines 3 and 6. Now remember, we always have access to lines that are earlier in a proof and which are not from a closed proof. So this one is from an open proof because we haven't closed, this first one, and it contradicts this, so we can cite them both. Okay. So now we have this. It's not the case that all X's are not F. Great, and that's what we were trying to show. So, we did our existential derivation ultimately, where we took this existential claim, we named the thing that it's about, right? Using our assumption, we named the F, which is the C, which is F, because we knew there was at least one X, which is F. And then we got what we were trying to show, right? Like we closed this proof, so now we have access to this show line. And so the 3 lines we cite are going to be 2, the existential claim where we got that we used to do the existential derivation. Cite line 3, where we named the thing that is F. We named it C. We made an assumption about it. And then line 4, where we proved what we were trying to prove. And look at that, everything closes, it's happy, it's good. This one's a bit difficult, but if you walk through what I've given you here yourself and you think about the steps as you go, hopefully it will start to make sense. But yeah, there you go. So that's a few examples of our new derivation rules. Okay, and here we are. We've finally finished the course, the Introduction to Symbolic Logic. So, once you have these tools down, everything we learned throughout the course, our derivations, our translations, our truth tables, finding main connectives, what all the symbols in the language mean, you have the tools now to do a whole lot of stuff in basic propositional and predicate logics. Again, make sure to keep up with the problem sets, do the extra practice I put on Brightspace to prepare for the final exam, ask questions at live sessions, the whole shebang. Just keep up with it, and it'll be all right on the final exam. And do note, if you decide to do more advanced logic at some point, I hope I've given you the tools required to start on that. Logic is really cool, and you can learn some really cool things about it, especially when you get to the more advanced stuff. So I hope that you can continue to have fun with it and use the tools that way. And yeah, thanks for watching all the lectures and doing all the coursework, and have a good future with logic. Thanks.